going through Brownian motion stochastic calculus, and he ended up with Ornstein-Uhlenbeck processes. And so this is a process which is quite slightly different from the geometric Brownian motion in that it's just got a gamma times the x. It's a dx jump, but the x is only in front of the t and it's not in front of the sigma, or the dB term, okay? So if this was geometric Brownian motion, you'd have something with a bracket round here and no gamma, so it's slightly different. Ornstein-Uhlenbeck comes up when later on in the course when you're modelling or writing down models for futures of interest rates, so modelling future interest rate behaviour. This is one of the models that is used to model future interest rates as opposed to stock prices. So this one works in a similar way to the standard way of solving it. You go in a similar way to if it was a deterministic system. You look for something which simplifies when you put an exponential in it. You get a very relatively simple equation, which now it's gone off the board, but you go through the solution process and you end up with that x at time t is x naught e to the minus gamma t plus sigma times some funny integral. Now the point of this is x naught is time now, and that's what we know. So the future xt depends on now with a discounted e to the minus gamma t plus a term times whatever this integral means. This integral is the stochastic part of the whole process. So the point is that this xt is not deterministic, it's a stochastic process, it's a random result. So you interpret this as saying this xt is a random variable with some deterministic component plus a random component, okay? And the random component here will determine, of course, really the distribution of what xt is. So this isn't saying that xt, you know, if you want to simulate what xt is, you would have to know what the distribution of this is, draw a number from that distribution, add this term, and that will give you an xt. So what you normally do is you normally say, well, what's the distribution of this xt? And so the distribution is going to be determined by this deterministic term plus the distribution over here. Now, the thing that you go on to do after that is you show, or there's a bit of a calculation here, which, let me just bring my thing up, it's gone to sleep. Right, so that's what Ornstein-Uhlenbeck is, and then the point is that you've then got the Ito. What we need to interpret what this function is. So we need to interpret what we mean by a general function of time integrated with respect to dB sub t. And in this part here, this bit shows that if you actually write it down in terms of a discretized time, dBt is just this difference of Brownian motions here. And this difference of Brownian motions, because it's standard Brownian, we know is distributed like n naught t over n, which is the time steps. That's just from standard Brownian motion definition. And so from the fact that we're basically adding up linear combinations of normal distributions, effectively this has got to be normally distributed as well. So the meaning of this integral means that it's a normally distributed variable, okay, with a certain mean and a certain variance. And you can go through and do the calculation and show that the expectation of that integral is 0. So that the mean is 0 of that normal distribution. And the variance then is going to be given by, well, if you do the variance calculation, it's just the expectation of the thing minus its expected value all squared. So when you work it all out, because that's 0, you just get the expectation of that squared integral here. But we still don't know how to do that integral here explicitly. But the magic, second most beautiful theorem in mathematics after Cauchy's theorem, and this is the thing that when I saw that theorem, I suddenly started to think that I understood stochastic analysis, okay, is Ito's isometry, which you can prove using a similar step-by-step process above. It basically says the expected value of a square of an integral of this form is just the expectation of the ordinary boring Riemann integral, but with the squared value inside. Okay, so this is a stochastic integral squared. You take the expectation, it's the same as the expectation of this squared, which if this is a deterministic function then is just the square of the ordinary boring deterministic integral, or rather the integrand squared integrated with respect to time, not with respect to this funny random process here. So this is the thing that turns stuff which we don't quite understand into stuff which is really understandable. Okay? So this is then the expectation of effectively that's the variance of this of that distribution. So the variance of this process is just this value here, and then finally plugging everything in. That should be a comma here. If it's not, is that a comma in the notes? I don't know. Is that a comma? Yeah, there's a comma there. It just doesn't show up. So there's a comma there, which means that whenever you've got an integral of this type, it's just a very snazzy way of saying this is a normally distributed variable with mean 0 and that variance. Okay? So that's basically turns gobbledygook into something that we can understand. Okay? Right. So we can use this now to work out what the distribution of the integrated Ornstein-Uhlenbeck process is. So this is what the integration of the Ornstein-Uhlenbeck stochastic differential equation gives us. So what we have to do is we observe that it's deterministic numbers. X naught is now, and we assume that we know what the value is now. T is the future. We discount gamma, we assume is just a constant we know, so this number is just a deterministic number that we know. This number has got exactly the form of that process over there, integral of g of s db sub s, that should be, sorry. I'm being pedantic. Okay. That's got the identical form to this over there with just a sigma in the front. So we know that this thing is presumably going to be somehow normally distributed. Why? Because if I had a constant onto a normally distributed variable, I've still got a normally distributed variable. Okay, it just shifts the mean over. So let me take the expectation of this value here. So then I have to take the expectation of this and the expectation of that, here and here. So sigma's a constant, it just comes out the front. This is just an ordinary number, so the expectation of an ordinary number is just the number itself, x naught e to the minus gamma t. This integral here has this form over here, so we know that the normal value, that it's normally distributed with mean 0. So the expectation of that, by definition, has to be 0. Okay? So the expectation of that process is 0. So the expected value of your Ornstein-Uhlenbeck is just x naught e to the minus gamma t. So that tells us something which we can then use later on. So now we think that this might be normally distributed. We know its expected value, and we're now going to work out what the variance is. So what's the variance? Well, it's just value process minus expectation all squared, expected value of. So here's my Ornstein-Uhlenbeck process. Here's my expectation, which from up this point here, this thing is automatically going to cancel off that thing just to leave us with this thing all squared. And then you're exactly in the same format as we've got here. We have something which is integrated with respect to dbt all squared, expected value of. And we use the Ito isometry to say, well, that's just the integral of the integrand squared evaluated using the normal integral, the dt Riemannian integral, time between a and b. So this thing here, when I do the expectation, well, first thing I can do is I'm integrating with respect to s here, effectively. The t is just something that comes out the front. So remember back to Math 1052, that's where the dummy variables come in. All right? So t is essentially, the s is a dummy variable. I'm integrating with respect to s and not t, so I can pull the e to the minus gamma t out. The squared gives me an e to the minus 2 gamma t. Then I've got left in here integral of e to the gamma s db sub s all squared. So then I apply the Ito isometry, and I take the thing in the side. This is my z, okay? That's my z. I have to square it, and then just integrate it with respect to the ordinary variable, not with respect to the random bit. So this is e to the 2 gamma s, because that's e to the squaring, that gives me e to the 2 gamma s ds. All right, I've written in terms of t's there, but that's just a dummy variable thing, but it's e to the 2 gamma s ds. So that integral is very easy to evaluate. That's just an ordinary integral. Well, first of all, the expectation of it, because this is just a deterministic numbers, the expectation is just the integral itself. Then I do the integral of this. This is just e to the 2 gamma s, which is e to the 2 gamma s on 2 gamma. It's an ordinary, boring, normal integral. Evaluate it between t and 0, and I get e to the 2 gamma t over 2 gamma minus 1, because it's e to the 2 gamma 0 over 2 gamma, multiplied through, and you get that as a result. So that is the variance of the Ornstein-Uhlenbeck process. So what we can then conclude is that Ornstein-Uhlenbeck is normally distributed, okay, because it's got the form something plus, so this bit's normally distributed. I'm adding something onto it, which is just deterministic, so that's fine. That's just a shifted normal distribution. The mean, x naught e to the minus gamma t, that's the bit, the deterministic bit I've added on. This is normally distributed with mean 0, and the variance is just what I've calculated there, and it's got that value here. So if you wanted to simulate an Ornstein-Uhlenbeck process in the computer or something like that, you don't have to, all this is just a coded form of saying, I just want to select, for my xt's will be selected from a normal distribution with that mean and that variance. That's all that long Ornstein-Uhlenbeck integrated formula just says. It's just coded format for a normally distributed thing with a certain mean and a certain variance. And that is so cool. I was so pleased when I first understood that. You're not that impressed. They all pretty much follow the same formula. You've got to look for the expected value, assume that it's, or confirm that it's normally distributed just from the format that you've got there. There's the expectation. The variance is then going to be the square of what's in here integrated with respect to time. It's all the same, always the same. Okay? And that gives you the answer. No? Look at some past exam papers, they're really quite fun. Don't you think that's amazing? Yeah, that's who knows what that means over here. But then you get a normally distributed thing there. That's so cool. Okay. Any questions on that? I'll do some examples on Friday. Right, okay, so let's now move on. That's the fun bit of the course. I'm annoyed I had to be away last week for that, because I enjoyed teaching. Right. Let's now go on to the general idea of what a derivative security is. All right, this is some waffly stuff before we get into some more maths again. Right. So there's the statement up there that they're the financial weapons of mass destruction from Warren Buffett, of course. But one of the first examples of a derivative comes from ancient Greece, actually. And Thales, not the arms company, but the philosopher, believed that that spring weather would be exceptionally favourable to olive growth. All right. So he negotiated the right to rent olive presses for the next harvest at a bargain rate from the press owners who wanted to hedge their bets against the poor market. So the olive press owners weren't sure what was going to happen in the future. Thales took an optimistic view and so said, look, I'll come and I'll rent them regardless of what happens from you, and so I can press the olives. And Thales, assuming that he was going to have a good harvest, he was betting that he was going to make a lot of money that way, because he was going to get those olive presses for a cheaper price than by waiting until the people found out. When spring came, there was a good harvest, so he'd rented them. He then took those actual olive presses, and he didn't actually use them himself. He sublet them to somebody else at a much higher price. Okay, so he didn't own them, but he sublet them, and therefore made a profit. That's probably one of the first examples of an option or a derivative security in history. So the point was, he didn't own the presses. He just was enabled to rent them at a lower rate because he took a bet on the market. When the market turned out to his favour, he was then able to rent them on for a much higher rate. He never owned the presses, but he owned the right to use them. He rented them at a higher rate and made a profit. And then at the end, of course, the press owners got their presses back again. Okay? The press owners were happy because they weren't sure of what the market was going to be, but at least they got some money in 6 months beforehand. Okay? So, what are the things we're going to be dealing with most commonly? Derivative securities are calls and puts. Those are some of the most common ones. So what are calls and what are puts? There's a lot of jargon here which has been developed by people who are not mathematicians and by people who just buy and sell. So some of it looks a bit strange why we would call it that, but that's just because it's common parlance before mathematicians got involved. So the first thing is vanilla products. Okay? Vanilla is like vanilla ice cream. It's the plainest, most boring ice cream that you can have. Okay? So vanilla just means an unexciting, ordinary, quite common derivative product. Okay? You'll see later on we have options which are called exotic options and things like that. We'll worry about those in a minute. But the simplest form of a derivative product is a vanilla option, and I'll explain why in a minute. We have calls and puts in vanilla options, and essentially the process of when we sell such options, you say you write an option. So if I'm going to sell an option to you, the jargon is I'm writing an option to you. Okay? I just write an option. Literally, it's like I would write something, contract down, and hand it to you. Okay? So that's why it's called writing. Options are generally traded on the underlying asset or based on the value of the underlying asset. So for Thales, the underlying asset there was the price of olives, okay, or the volume of olives available, okay. But usually it's something to do with like a share. It might be a commodity. It might be a stock index like the FTSE or something like that. So the underlying is the thing that the derivative product is based on. But the point is that you're not actually necessarily trading the underlying asset, you're trading something that is based or derived from the value of the underlying product. So that's why it's called a derivative product. It derives its value from an underlying product, but it doesn't, so it's separate from the underlying product, but its value depends on the underlying value of the product. There's an expiry date associated with them, so they expire. There's an end at which the contract ends. That's usually denoted by a capital T. And in European vanilla calls, vanilla calls and puts, you have things called strike prices. So a strike price, usually denoted by K, is basically a value at which something happens. It's a trigger value at which you either start to earn money or you don't earn money at all. Okay, generally something like that. Expiry is usually given as a month. So when you look it up, you'll see it's a January call or March call or a July call or something like that. And the actual day of each expiry depends on the exchange and what you're trading, but it's often something like the third Friday of each month or the third Friday of the third month or something like that. So, let's now define two very, very basic options. A European call, okay, now why is it called European? I don't know. Probably because it was first traded in Europe, right? European means, and there's a very specific meaning to European, which I'll explain. A European call on an underlying asset gives the holder, that's you, I've written it to you, you're the holder, it gives you the right, but key point, not the obligation. You can have a right, but not an obligation, to buy the underlying asset at the price, strike price K, at the expiry time T. Okay? So if I sell you a European option to buy my house, say, okay, you can buy my house with a strike price of, say, £300,000, 10 years in the future, okay, regardless of what the actual price of my house is. So, if the price of my house on the market was £500,000 in 10 years' time, you could come to me with that contract and say, I have a contract with you to sell me your house for £300,000. Now, you have the right to do that, I have to comply. That was the contract. If, though, my house in 10 years' time is only worth £200,000, you are not going to come to me and ask me to sell it to you for £300,000. You would be rather stupid to do that, because you could buy it on the market for £200,000. Okay? So, under those circumstances, you choose not to exercise that option. You have the right, but not the obligation to exercise. So basically, it's more of a one-sided deal. If you come to me, I have to sell you my house. But if you don't come to me, there's no consequence for you. Okay? The only consequences we'll see later on is you'll have lost your money for buying the premium up front, for buying that option, but that's the only option. Okay, so generally you buy a call when you think the price is going up. Why? Because, well, we'll see that in a minute. Conversely, a European put option on an underlying gives the holder the right, but not the obligation, to sell the underlying asset at a price K at time T. All right? So, let me think that you buy a car. Okay, you've got a car, and I sell you a put option on that car. That gives you the right, but not the obligation, to sell me that car for, say, £5,000 in a year's time, say. Now, I don't know what the price of the car is going to be in a year's time, but you've got the right, but not the obligation, to sell it to me for £5,000 in a year's time. So let's say that the car, as usually happens, depreciates. Let's say the car is only worth £3,000 in a year's time. You have the right to come to me as the writer of the option to say, you've got to buy that car from me for £5,000. And I, because I've sold the contract, it's a contract, it's a one-sided contract, I have to buy that car from you for £5,000. So, if the car, however, goes up in value, let's say it's a Bentley or something like that, and it goes up in value, and say it's worth £10,000, okay, you're not going to come to me and ask me to buy that Bentley from you for £5,000, because you can sell it to the market for £10,000, okay, if the price goes up. So at that point, your put option expires worthless. You're not going to exercise it, but you don't have to. That's your right to do that. So you'll lose the money that you cost to buy the put option, but other than that, you don't have to exercise it. So a call option you buy if you think the price is going up. A put option you buy if you think the price is going to go down. Okay. Now, why is it called European? European means that there is one and only one time at which you can exercise that price, that option. So there's an expiry date at which you must then decide whether you exercise that option or not. You cannot exercise it before that expiry date. You can only exercise it at the expiry time. Okay? So that is just what European means. Don't know why, but that's what it's called. So that is a European option. An American option is something very similar. Well, it's something in some way similar, but the difference between an American call option or an American put option is that you can exercise that option at any time between the time that you buy it and the time of expiry. So European only at the end, American any time throughout. So the American option has more freedom. Haha, American. Right. It's got more freedom than the European, someone who lives in Europe. But you can then, you've got more freedom to exercise at any time. So naturally, you would expect perhaps American costs more. An American option you think will cost at least as much as a European option, because as a one-sided contract, you're getting quite a good deal potentially out of this. So that you have to, for a fair price, you have to buy this option. So you'd expect that the price of an American option is going to be more because you've got more freedom to do that. Okay. Right, so essentially this is a valuable thing that you possess because you have the right to do, basically what you're doing is you're taking out, you could regard it as two ways. You could regard it as you're betting on the future, and you know when you bet you have to put money down as a stake, Or you could regard this as an insurance. So basically you're trying to basically cut your losses in a scenario because you don't, if you think that something is, if you think you've got to buy something at some point in the future and the price is going up, purchasing an option will allow you to fix the price at which you buy that option, at which you buy that product, okay? So that's like buying an insurance or buying a privilege. So you would expect to have to pay me something as to write to actually to write you that option, okay? Of course, I've got the exposure to do with that, either with my house or whether I've got to buy your car or something like that. So I have to be compensated for that risk. Okay, what I do with that money is up to me, but if I'm sensible, there is a proper trading strategy that I should carry out, which will mean magically that I can take that risk away. That's ultimately what we're going to be working towards, because ultimately what I do with that money, if I carry out the correct trading strategy, that will tell me how much money I have to charge you. Okay, and that's actually how everything goes around and make sure that this all works. But we'll do that later on. So again, it's a one-sided contract because I have an obligation to settle up. If I write you that contract, I have to go through with that contract. If I don't, I get kicked off the market. If I'm trading on a derivatives market and I don't basically fulfill that contract, I can be kicked off the market. But you as the holder, you have no obligation. It's purely up to you whether you exercise or whether you do not exercise that option. So it's a very one-sided operation. Normally, you don't actually trade shares. Okay, this is about buying shares or buying underlying assets or things like that. You can do that if you want to. So if you are, for example, doing want to know that you're going to do some foreign exchange deal in 3 months' time, if you're the chief accountant of a company, you might buy an option to buy US dollars at a fixed rate in pounds. Why? Because then whatever the stock market is, you basically fixed in the maximum price you're going to be paying for those dollars to do that financial deal in 3 months' time. So you might want to buy some dollars or something in 3 months' time, but you could do it as a straight bet. You could be just doing it for betting reasons. Like Thales thought that he guessed what the market was going to do in terms of olives. But that's purely up to who does it. There's also the idea I mentioned about eliminating risk. That's called hedging. All right, so hedging your bets in common speak. Hedging is about eliminating risk, and as I said, there's a very proper trading strategy that I, as a writer, should carry out to eliminate my risk, and I'll do that later on with you. This is linked to things that are spread bets, which you look at my publication record, you'll see I have published on. Right, big money is spent on it. These lecture notes were originally written when you were probably still in primary school, and it was about $10 to the $13 in 1990s when that was done, but it's a lot more money now that people use. Okay, so let's do a simple example of the use of an option. Okay, as you can see, when this was 1999, when these lecture notes were originally written. So I've got various companies. Okay, now here's an example of something called Life options. Life was the London Futures Exchange, effectively. It's been taken over now. I think it's part of Euronext, which is a European exchange. And like when you look in the Financial Times, you'll see the name of the company, and if it's a shares, you'll just see the share price. Here you can see things like January, April, July call options, January, April, July put options. Okay, so this lists the value. This is when it was all done on paper. Of course, it's now computerized. I'll show you that in a bit. This will give you, it'll say that an Asda January call option with a strike price of 140 will cost you 23.5p. Okay, something like that. So the first thing to observe is that the call options cost a lot less generally than the actual value of the underlying product, which is some or underlying asset, which is one of the reasons why they're useful for speculating or for gearing. So let's suppose that we've got, if you go back, you've got, let's look at Asda shares. Okay, and at the time, let's suppose we're at time now, and let's suppose, so the price is 158p, okay, and we've got Zenica, which again doesn't exist anymore, I think, but S0, the price was 2297.5 pence, okay, so that's the time now. So what's the history? We've got Asda, we look at the history, we say Asda, let's say it's been rising steadily, but has dropped by about a quarter in the last period, last year. And so the stockbrokers are saying, well, don't buy it anymore, hold it, because it might go up again, okay? But we're not sure what's happening. 4 directors have sold shares in the last 5 months, which is not a good sign. So they're obviously trying to get their money before it goes down. So the prediction here is that shares will go down. This, of course, is a purely fictitious example, if anyone is recording this. This is purely fictitious and it's just made up, all right? So the profit, therefore, if it's going down and we're interested in doing some option trading, because it's going down, we're looking to buy puts, okay? Because we think we can make money with options when the thing goes down. Right, so if we look at this thing here, value, what do we have? Current price is 158. January puts with a strike of 160. Yeah, we've got 160 is, what was it? 12.5p. Right, so if I zoom in here, here's Asda, here's a 160 strike. A January put is 23.5p. Okay? So, I'm looking to do a trade over the period till January. That's 12, no, there should be 12.5. Oh yeah, sorry, there's a January put, sorry, 12.5, sorry. Put January 12.5 here, okay? So, this is 12.5p, okay? So let's say that I'm going to buy a January put with a strike price of 160, and I'm going to buy 4,000 of them at 12.5p, which is going to cost me £500. So I spend £500 buying 4,000 put options at 12.5p. So that will give me the right, but not the obligation, to sell Asda 4,000 Asda shares at 160p at the expiry date in January, in 3 months' time. Okay? So it will cost me £500 for that right. We'll see in a minute. On the other hand, then let's look at Zenica. So Zenica reckons it's underpriced. There was some new drug that came on the market back in October. So this is quite a good drug apparently. So the prediction is the shares are going to go up. So what am I going to do? Well, the share price is 2297. That's quite a lot actually, 23 pounds nearly for each share. But I can get January calls are on sale at say 200p with a strike of 2,200. So let me just check what that is. So if we go to Zenica, there, okay. So Zenica, here's the 2,200 strike column. This is the January column, 199.5. So I'll call that 200 for the calculation. So let me look at that. So I can do with Zenica then, I'm going to buy January calls with a strike price of 2,200. Okay, and what am I going to do? I'll buy, let's say, 500 of them at 200 pence, so that's going to cost me £1,000. So basically what I'm doing is I'm going to put £500 into put options for Asda and £1,000 into call options for Zenica. Okay, so let's now roll forward to January. January comes. And let's see what happens. So in January, the share price of Asda was 161.25 pence. S sub T means the share price at expiry. So the expiry date was January. So S sub T of AstraZeneca was 2617. Right, so what am I going to do? I've got put options for Astra, call options for AstraZeneca. Am I going to exercise the put options? Hands up who thinks I should exercise the put option. Hands up who thinks I'm not going to exercise them. Hands up who doesn't know. Right. So I basically, a put option gives me the right but not the obligation to sell something at a particular price. The put options I bought was at 106, that I could sell them, the shares at 160. So there's no way I'm going to bother to sell any shares that I can get hold of for 160 pence if I could sell them in the market for 161 pence. Because by selling them to the market directly, rather than the person who wrote that option, I can get more money. Okay? So, these ones, that expires worthless. So the option, the put options expire worthless because ST is greater than K. So if the expiry price is greater than the strike price for a put option, you don't bother. Okay? So what I do is, if I do it here, so my loss, profit loss, my profit or loss then is, well, I've lost £500. I've lost all the investment I put into those put options, okay? Which is slightly worrying, 100% loss. Okay, let's have a look at this one though. So now let's go back to the Zeneca one. So Zeneca, current price is 2617. The options I bought allow me to buy things for 2,200. Okay, so what am I going to do? I'm going to exercise them. Why? Because I can buy something for 2,200 from the person who wrote me the option and immediately sell it to the market for 2,617. So here's another thing that you have to worry about slightly when you're doing options, is you say, well, how can I get the money to buy all this? Well, if you're trading on account, you don't necessarily need the money, okay? Because you can buy it, or if you like, you can think about it as borrowing the money immediately, buying it, immediately selling, and then immediately sorting your money out. If you're trading on account, you'll have a certain time period in which you do that trading. So you can say, right, I'm going to buy 2,200, I'll have to pay people for that, but I don't have to do that until the settlement date. If I immediately sell for 2,617, I've got the money that I need, and I could actually pay the person off now, or wait until the settlement date and pay them off, having stuck the money in the bank somewhere and get some interest. So that's allowed. So in theory, I might have to do that buying and selling. In practice, what I could just do is I could just say to the person, I could say, well, let's just effectively, you give me the difference of the value between the two. Okay? Because I can buy those shares from that person for 2,200, immediately sell them to the market for 2,617, and then I would make the difference. So the profit I get here is I exercise and make, well, for each option, I can make this amount of profit. So I make 417 pence per option. How many options have I got? I've got 500. So 500 times 417 is £2,085. This is in pence, so you can write that as £4.17. So 500 times £4.17 is 2,085. So I make £2,085 from £1,000 investment. So my profit is 2,085 minus 1,000. So I make £1,085 from that deal. Look at the percentages. On that one, whoops, I lost absolutely everything. All my put options expired worthless. It cost me £500. I've lost the lot. On this one, I've made 1,085 profit. No, wait a minute. No, what have I done? That's missed profit. So wait a minute. I put 1,000 in. I got 2,000 back. I've turned £1,000 into 2,000 and no, what have I done? No, I turned £1,000 into £2,000, so I should have 100. Yeah, I've got 100 and 8% profit. Okay. So what you can see is this is quite a large percentage profit. If I add all of this up, I've got £585, and here you see I had 585, the total percentage profit on the total deal was, I basically made a profit of 585 on an investment of 1,500, because I put 500 in there, 1,000 in there, so I got 1,500 in total. I've got 585 over 1,500, which is about 39%. So I could have put that money in the Yorkshire Building Society and got 1.5% in an ISA. Or I can play games on the stock market and get 39% return. Okay. Depends on how risky you like to be. Because if this one had gone the other way, I would have had 100% loss here as well, and I'd have lost all my money. It's only because that price went up. If that price had dropped below the strike price, I'd have lost all my money again on that one. So this example is constructed to show shares are very, options are quite fun, but they're very dangerous. You can lose all your money, or you can make a lot of profit. Okay, they magnify the profits. It's called gearing that you can get. You can actually work out what the price would have been as if you'd have bought the shares and how much you would have then made, and it would have cost you a lot more money. Because why? Because the shares themselves, say for example here, you'd have had to have spent, to buy 500 shares, you've got to do 500 times 2297, which is a hell of a lot of money, in comparison with just £1,000. Okay? So 500 times, to buy the shares to do that thing would have cost you a lot more money up front than buying the options. So the percentage gain you would have had would have been less by buying the shares than if you'd have bought the options. So that shows you that options are quite magnifying, they gear your initial investment quite a lot, which is why they're superficially appealing to psychopaths who like trading and making lots of money. But the consequences are you can lose absolutely everything as well that you invest. Right, I think we'll leave it there and then pick it up tomorrow. Okay?